Way back in lecture 2 of this course, I introduced the concept of your home as an integrated assemblage of 8 major engineered subsystems. Since then, we've actually examined 6 of those subsystems: structural, foundation, building envelope, site, plumbing, and electrical. In this lecture, we'll be looking at the 7th: heating, ventilating, and air conditioning, or HVAC. Today, I'll actually be focusing primarily on heating systems and on the integration of heating with air conditioning technologies as we discussed in the last lecture. And then next time, we'll touch on ventilation in conjunction with a broader discussion of energy efficiency in residential construction. So let's get started. A residential heating system consists of 3 major components: a device for converting chemical or electrical energy into heat, a means of distributing that heat throughout the building, and a mechanism for controlling the system such that the desired temperature is maintained. If the building is cooled as well as heated, then an air conditioning system might also be integrated within the heating system, though this isn't always the case. We'll begin by examining the familiar device that's used to control your home's inside temperature, the thermostat. This is a simple yet vitally important technology, not only for home heating, but also for temperature control in your refrigerator, your oven, iron, a host of other common devices, including your automobile. Now, no doubt, you've operated many thermostats: older mechanical ones, like this one, and newer digital ones, like this. And when you set the temperature on the outside, what's going on inside? Well, at its very heart, every thermostat must have an element that's capable of sensing and responding to changes in temperature. In most thermostats, the design of this element is based on a natural phenomenon we've already encountered several times in this course: the thermal expansion and contraction of materials. Now, as you know, all materials expand when they get hotter and they contract when they get cooler. What you might not know is that different materials, like these steel and brass strips, expand and contract at different rates. The actual amount of thermal deformation for a given temperature change can be calculated quite accurately using this equation and a material property called the coefficient of thermal expansion. The coefficients of thermal expansion for steel and brass can be obtained from materials handbooks and are shown here. Therefore, for these 12-inch long bars, a temperature change of 50 degrees Fahrenheit would cause the steel to elongate by 0.004 inches and the brass to elongate by 0.006 inches. And so there's good news and bad news. The good news is that thermal deformation is both predictable and easy to calculate. The bad news is that the actual amount of deformation is so minuscule that it would be extremely difficult to use as the basis for temperature sensing in a simple household device like a thermostat. But we can overcome this limitation by bonding these same 2 materials together, as I have here, to create something called a bimetallic strip. Now, that bond can either be glue or, in my case, I have the 2 pieces of metal screwed together, but you can see we have brass strip on one side and the steel strip on the other. When I heat this composite bar, the brass is going to try to expand more than the steel, as you can see in this diagram. But it can't actually do this because the bond between the 2 metals constrains them to expand equally along the plane of the connection. As a result, the bar will bend like this to accommodate the 2 different expansion rates while still maintaining the bond. In my diagram, I've exaggerated the bending effect so you can see that the center line of the brass here is indeed longer than the center line of the steel here. Now, I can't actually fire up my torch here in the studio, so let's watch this video that illustrates how the bimetallic strip actually works. Here I'm adding heat to the bar, and as it heats up, if you look very closely, you can see that it begins to bend. The effect clearly is quite subtle, but it's very important to recognize that the amount of bending is large enough to be measurable, in sharp contrast with the longitudinal expansion of either metal, which we've already calculated to be less than 1/100th of an inch. Now, in a bimetallic strip, the amount of bending for a given temperature change depends on both the length and thickness of the strip. A longer, thinner strip bends more than a shorter, thicker one. And that's why most thermostats use a very long, thin bimetallic strip that's been formed into a coil so it can fit within the thermostat housing. Watch how much thermally induced bending this coil experiences with just a modest input of heat. The effect really is quite dramatic. Now, here's how the bimetallic coil works in a typical mechanical thermostat. This lever is used to set the temperature. As the lever is rotated, the bimetallic coil rotates along with it, as does this electrical contact. A second electrical contact is fixed to the body of the thermostat here. The two metals of this bimetallic coil are arranged such that a temperature increase causes the coil to unwind, and a temperature decrease causes it to wind tighter. Thus, as the room temperature falls, the moving contact gets closer to the stationary one. When the two contacts are very close, this magnet pulls them together, closing the circuit and signaling the heating system to switch on. Now, as the temperature in the room begins to rise, the coil tries to unwind, but initially it's prevented from doing so by the magnet. Eventually, as the temperature continues to increase, the bending force in the coil gets strong enough to overcome the magnet, and the contacts pull apart. The circuit is now broken, the heat shuts off, and the cycle starts anew. Now notice the two important functions performed by the magnet. First, it ensures that there's a very solid electrical connection between the two contacts whenever the circuit is closed. Second, it produces an effect called hysteresis. The magnet lengthens the system's cycle time by allowing the temperature to increase a few degrees above the set point before opening the circuit. If it weren't for hysteresis, the system would cycle on and off much more rapidly, causing decreased efficiency and increased wear. Hysteresis is a common feature of many automated control systems for which short cycle times would be problematic. Now, before we can examine the heating system itself, we need to review a few key concepts about heat. As we learned in previous lectures, heat is the spontaneous transfer of energy from a hot region to a cold region. But how does this process actually happen? Well, heat transfer can occur in any of three different modes: conduction, thermal radiation, and convection. Conduction is heat transfer through a substance or through physical contact between substances. When I place one end of a steel poker into my fireplace, heat is conducted from molecule to molecule along the length of the bar, and very soon the handle feels quite hot. Thermal radiation is heat transfer through electromagnetic waves emitted by a substance. When you sit in front of a fireplace and feel the warmth on your face, you're experiencing heat transfer by radiation. Unlike conduction, radiation doesn't require an intervening medium for transmission. It can even move through a vacuum. The third form, convection, is heat transfer through the movement of a liquid or gas. There are two types. Natural convection is fluid movement caused by differences in density, like hot air rising through a chimney, while forced convection is externally driven, for example, by a pump or a fan. Understanding these three modes of heat transfer will help us appreciate not only how heating and air conditioning systems distribute heat throughout your home, but also how various components of the building envelope, like insulation, windows, and foundation walls, resist heat transfer with varying levels of effectiveness. There are three principal types of modern whole house residential heating: the furnace, with heat distributed by forced air; the boiler, with heat distributed by circulating water; and the heat pump, usually with forced air distribution as well. The furnace with forced air distribution, illustrated here, is the most common heating system used in North America. The furnace can be fueled by natural gas, propane, or heating oil. This gas furnace has four main components: the burner, electric blower, heat exchanger, and control system. When your thermostat calls for heat, the control system opens a valve, sending gas to the burner where it's ignited by a pilot light. Outside air is drawn by natural convection through an intake pipe to provide oxygen for combustion. The resulting hot combustion gases flow upward through the heat exchanger and are then exhausted out through a stack that extends through the roof or wall. Meanwhile, once the burner is going strong, the blower switches on, drawing air from the main return duct through a filter and then up through the heat exchanger where it's heated by those exhaust gases rising up from the burner. This stream of hot air is then propelled by the blower into the main supply duct called a plenum. And by the way, the term blower refers to a centrifugal fan, one in which air enters here along the axis of rotation, then is accelerated radially by the spinning blades of an impeller, and then exits the housing tangentially, like this. Blowers are quite common in many types of heating, ventilating, and air conditioning equipment. Now note that two completely separate streams of air are moving through the furnace. Combustion air, which originates outside the house, feeds the flame and then is exhausted through the stack. And circulating air, which originates from and returns to the home's occupied spaces. The heat exchanger's job is to transfer heat from one stream to the other without allowing any intermixing, so those noxious combustion fumes won't contaminate the air we breathe. This heat transfer occurs primarily by conduction through the heat exchanger's metal walls. An oil-fired furnace works essentially the same way, except for the combustion system. Here, a motor-driven pump sends heating oil to a burner, which sprays fine droplets of fuel into a combustion chamber, and then ignites the fuel-air mixture with high-voltage electrodes. In either case, the two energy inputs, the combustion of fossil fuel and the electricity required to spin the blower, produce a steady stream of hot air, which is propelled by the blower through these supply ducts into individual rooms. And then heat transfer occurs by forced convection. In many homes, the distribution ducts are partitioned into two or more zones, each with its own thermostat, so that different areas of the house can be maintained at different temperatures. The flow of hot air into each zone is regulated by a damper, which is controlled by signals from a zone control panel, as shown here. Supplying an adequate quantity of warm air to your home's occupied spaces is only half of the distribution system's job. To maintain proper circulation, an equal quantity of air must be pulled back to the furnace through a parallel set of return ducts, again propelled by the blower. At the point where each supply and return duct penetrates an interior wall, there's an adjustable vent called a register, which allows you to control the flow of air into and out of each heated space. Now, a common problem with forced air heating systems is their susceptibility to air pressure imbalances, which can be caused by improperly adjusted registers, leaky ducts, or faulty duct configurations. The key to avoiding pressure imbalances is ensuring that the quantity of warm air supplied to each heated space is equal to the quantity of return air pulled from it. Let's look at three common situations where this doesn't happen. Here, a leaky supply duct results in more air flowing from the heated room than into it. Thus, the pressure of the heated room is too low, and the pressure of the unheated basement is too high. This pressure imbalance causes cold air to infiltrate into the heated space from both the basement and the outside through unsealed gaps in the building envelope. Here, a leaky return duct produces the opposite effect: high pressure in the heated space and low pressure below, causing warm air to be forced out of the heated space. And here's the faulty duct configuration problem, caused when the builder saves a few bucks by placing one large return duct in the hallway and none in the individual rooms. This arrangement might work reasonably well when the doors are open, but when they're closed, substantial imbalances develop between the rooms and the hallway. All of these problems can be fixed. So if you have a forced air system and you're experiencing drafts and air infiltration, you might want to call a reputable HVAC contractor and get your ducts in a row. Another common complaint about forced air systems is that they produce excessively dry interior air, leading to dry skin, sore throats, greater susceptibility to respiratory ailments, and excessive shrinkage of wooden floors and trim. An effective remedy is to install a whole house humidifier, which attaches directly to your main supply plenum, like this, and adds moisture to the circulating air. But don't overdo it. As we discussed in the lecture on the building envelope, if your home's interior air is excessively moist, water can condense inside the wall cavities, leading to the growth of mold. This chart shows the National Research Council's recommended maximum relative humidity for interior air for various exterior temperatures. As you can see, as it gets colder outside, you need to maintain lower interior humidity to avoid problems. But how do you measure the relative humidity of your inside air? Well, actually, many modern thermostats will do it for you. But if yours doesn't have this capability, don't worry. All you really need to do is watch your windows. When you see moisture condensing on the inside surfaces during cold weather, it's time to turn down the humidifier or dehumidify. Given these challenges, you may be wondering why forced air heating is so popular in the US. The answer is certainly that in forced air systems, a single set of ductwork can be used for heating, cooling, air filtering, and humidification, an efficiency that greatly simplifies installation and thus saves money. Now, we've already seen how filtering and humidification are integrated with heating, but what about cooling? Well, this model shows a standard central air conditioner called a split system because the compressor, condenser, and expansion valve are located in a standalone unit outside while the evaporator is indoors. And note that in an integrated system, the evaporator is actually placed inside the supply plenum, just above the furnace. Thus, when the air conditioning system is operating, cool air is circulated through the same ducts used by the heating system, and it's propelled by the same blower. It's a very efficient setup that accounts in large measure for the popularity of forced air heating systems in climates that require both heating and air conditioning. Now, our second major type of heating system is the boiler with hot water distribution, also called hydronic heating. This type is the norm in Europe and was quite common in the US until widespread adoption of central air conditioning prompted the shift to forced air systems. And today it's staging a comeback in the US, thanks to the growing popularity of radiant floor heating. At the heart of every hydronic heating system is a boiler, fueled by natural gas, propane, or heating oil. The boiler works just like the furnace in a forced air system, except that water rather than air circulates through the heat exchanger and the distribution system. The pipes of the distribution system are arranged in closed loops, one per zone, with water circulated by one thermostatically controlled pump for each loop. In the occupied spaces, radiators or baseboards are used to transfer heat to the surrounding air, primarily by natural convection. Yes, I hate to burst your convective bubble, but yes, contrary to its name, a radiator actually transfers relatively little heat by radiation. Three other unique aspects of hydronic heating systems are worthy of note. First, because water in the closed distribution loops expands as it heats, the system includes an expansion tank to accommodate the water's changing volume. Second, to compensate for leaks and evaporation, the system is connected to the home's main water supply line with inflow controlled by an automatic valve. And third, unlike forced air, hydronic heating can be integrated with the domestic hot water supply system. The most common technology for accomplishing this interconnection is the indirect water heater, a heavily insulated tank that's heated by one loop of the hydronic system set up as a separate zone. A heat exchanger transfers heat to the potable water without allowing the two streams to mix. Hydronic heating has a number of advantages over forced air heating. From the builder's perspective, Those small diameter water pipes are much easier to route through walls than large ducts. And it's somewhat easier to configure and control separate zones in a hydronic system. From the occupant's perspective, hydronic systems produce more even distribution of heat, and they don't cause air pressure imbalances. On the negative side, hydronic heating is generally less responsive than forced air heating. When your thermostat calls for heat, it takes a while to get those radiators warmed up. There's also the danger of water damage due to leaking pipes. And while hydronic cooling is now commonplace in Europe, it's still not widely available in the US, so separate ductwork is typically required for air conditioning. As I noted earlier, hydronic systems are currently making a comeback in the US because of their compatibility with radiant floor heating. Although the concept of heating an interior space through the floor is actually quite ancient, modern radiant flooring didn't really catch on until recent emphasis on energy efficiency stimulated renewed interest in this technology. More on this in a moment. Today's hydronic radiant floor systems are constructed by embedding polyethylene tubing, like this stuff, within a concrete slab or within the wooden floor framing. Here's a typical installation, with tightly spaced loops of tubing distributed over the entire floor area prior to being encased in concrete. The tubing is connected to the boiler through a manifold like this one. In operation, moderately hot water from the boiler is pumped through the tubing, heating the entire floor slab by conduction. The slab in turn heats the room by a combination of radiation, conduction, and convection, with more heat transfer by radiation than any other form of heating, except perhaps the fireplace. And herein lies the source of the energy efficiency that's prompting so much enthusiasm for radiant flooring. It turns out that heat transfer by radiation makes us feel warmer than heat transfer by convection. You actually experience this every time you sit by a campfire. Did you ever wonder why, as you look at the fire, your face feels warmer than your back, even though the air temperature in both places is the same? The answer is that your face is receiving radiant energy directly from the fire, not through contact with the air. Radiant flooring produces the same perception of thermal comfort, and the effect is further enhanced by the conduction from the floor directly into your feet. Thus, in comparison with convection-based systems like forced air and conventional hydronics, radiant flooring allows you to set the thermostat significantly lower and still experience the same level of thermal comfort while also saving a lot of energy. Radiant floor heating is also quiet and clean. It doesn't produce drafts, and it doesn't clutter up your house with baseboards or vents. On the downside, radiant systems are significantly more expensive to install than other types. Okay, now let's turn to our final form of home heating technology, the heat pump. In the previous lecture, I noted that the heat pump is essentially an air conditioner that's been turned inside out. But what does this really mean? Well, in an air conditioner, the condenser, which transfers heat from the refrigerant into the warm region, must be oriented toward the exterior of the house. But in a heat pump, the condenser is oriented toward the interior. Similarly, the evaporator, which transfers heat from the cold region to the refrigerant, is oriented toward the interior in an air conditioner, but toward the exterior in a heat pump. Otherwise, heat pumps and air conditioners operate in exactly the same way. And a great advantage of this technology is that one system can be used for both heating and cooling, an arrangement that can save both installation cost and space. But how does a combined heat pump air conditioning system really work? When the system is switched from the heating mode to the air conditioning mode, do the condenser and evaporator physically change places? Well, no. Recall that both of these devices are just heat exchangers. Each is really just a copper coil with a fan blowing across it. Thus, in a combined heat pump air conditioner, each coil can be used as either a condenser or an evaporator. And the only mechanical action required to switch between cooling and heating is to reverse the direction of the refrigerant flow. This is accomplished quite elegantly with the aid of a few cleverly designed valves. Heat pump systems have the added advantage of using one set of ducts for heating, cooling, humidification, and air filtering, just like forced air systems. Now, as an engineer, I can't help but feel a certain affinity for this sort of elegance in engineering design. For this system's ability to deliver either heating or cooling using essentially the same mechanical apparatus with the flip of a switch. Modern heat pumps also have very high thermodynamic efficiency. For these reasons, in moderate climates requiring both heating and air conditioning, a heat pump can be quite cost effective. Yet, as we've seen so often in this course, there is simply no such thing as a perfect technology. Like all engineered systems, the heat pump also has some significant performance limitations. Most importantly, its heating performance drops off sharply when the outside air temperature dips below 30 degrees Fahrenheit. This problem is an inherent limitation of the vapor compression cycle. At the most fundamental level, the system relies on a transfer of heat from the outside air into the refrigerant, thus causing the refrigerant to boil. As the outside temperature drops, it gets closer and closer to the refrigerant's boiling point, and this heat transfer becomes progressively less effective. For this reason, when a heat pump is used in a cold climate, a system usually includes supplemental electrical resistance heating, which kicks in automatically when the mercury falls below a programmed threshold. Electrical resistance heating tends to be very expensive, so much of the heat pump's efficiency can be lost in a deep freeze. Now, I should note that the device I've been calling a heat pump is more properly called an air source heat pump, to distinguish it from an exciting new technology called the ground source or geothermal heat pump. Well, actually, this technology isn't really new. The first ground source heat pump was actually built in the 1940s. But it is new to most of us because it wasn't widely adopted outside of Scandinavia until the early 21st century. And once again, the rapidly increasing popularity of this groundbreaking technology is being driven primarily by growing interest in energy efficiency. The ground source heat pump uses the earth rather than the outside air as its heat source in the winter and its heat sink in the summer. This technology exploits a simple geophysical phenomenon that the underground temperature of the earth is lower than the air temperature in the summer and higher than the air temperature in the winter. As we've seen, a heat pump interacts with the outside world through its exterior coil, which serves as a condenser in the cooling mode and an evaporator in the heating mode. In the cooling mode, the coil transfers heat from the refrigerant to the surrounding environment, causing the refrigerant to cool and condense. Reducing the temperature of the surrounding environment then significantly increases the efficiency of this process. Conversely, in the heating mode, the coil transfers heat from the surrounding environment into the refrigerant, causing the refrigerant to boil. Here, raising the temperature of the surrounding environment also enhances the efficiency of the process, while also eliminating the principal limitation of air source heat pumps, their sharp decline in heating performance when the outside air temperature drops below freezing. In an actual geothermal system, the role of the exterior coil is performed by a long loop of polyethylene pipe buried below the frost line as shown here. A pump circulates a mixture of water and antifreeze through this ground loop, and a heat exchanger is used to transfer heat between the ground loop and the refrigerant loop used by the heat pump. Beyond this point, the system works just like an air source heat pump, though with significantly less electrical power required to run the compressor. Ground source heating and cooling is certainly not a panacea. It's generally quite expensive to install, and its effectiveness is strongly influenced by the type and moisture content of the soil. Wet soils are favorable for heat transfer between the soil and the circulating fluid, while dry soils are not. Expansive soils like clay are particularly problematic because they can contract away from the underground tubing, leaving an air void that drastically reduces heat transfer. These limitations notwithstanding, the ground source heat pump is among the most economical and environmentally friendly options for whole house heating currently available. If I were building a new home today, I would certainly be considering this option. But a word of caution, please. If you're interested in pursuing enhanced energy efficiency, either in a new home or an existing one, it's critically important to look beyond the heating and cooling systems. Achieving optimum energy efficiency in your home requires a more holistic approach that should include insulating, preventing air infiltration, selecting windows and doors, and using energy efficient appliances, and might even include rethinking some of the most fundamental aspects of conventional home design. We'll consider this approach in the next lecture as we examine the brave new world of the green building movement. In this lecture, we'll be exploring one of the most important trends in modern residential construction, the green building movement, which advocates the design and construction of buildings that use natural resources more efficiently while minimizing adverse impacts on our environment. Green building is a broad, holistic approach that seeks to minimize energy consumption, maximize the use of renewables and recycled materials, minimize water consumption, minimize or eliminate emissions, improve indoor air quality, and reduce waste. Here we'll focus on the most important dimension of green building, minimizing energy consumption. And then we'll return to the other dimensions when we look more broadly at the subject of sustainability at the end of this course. Now, it's hard to say exactly when the green building movement began. Certainly, the trend toward increased energy efficiency has been underway at least since the energy crisis of the 1970s. And the movement has gained considerable momentum in the past decade as governments, industry groups, professional societies, and the public have become increasingly aware of both the environmental and economic benefits of sustainable development. During this period, governments at all levels have established incentive programs for green construction. Professional organizations have established technical standards and certification programs. Successive editions of the International Residential Code have added progressively more stringent provisions for energy efficiency while also accommodating new green building technologies. The emerging field of building science has provided much needed research to support these new developments, and most importantly, consumers in increasing numbers have begun demanding greener homes. But can we really make significant reductions in global energy consumption by just changing the way we build individual homes? Well, in a word, yes. In the US, the residential sector accounts for 22% of total energy consumption and 37% of electric power consumption. Thus, even modest gains in residential energy efficiency really can make a substantial difference in our overall energy picture. And as we'll see in the next two lectures, achieving modest gains is neither difficult nor expensive, particularly for new construction. During this lecture, we'll look at the basics of energy efficiency. And then in the next, we'll go beyond the basics as we explore a fundamentally new approach to green building called passive solar design. Through these lectures, I hope you'll find, as I have, that pursuing enhanced energy efficiency isn't just economically beneficial and socially responsible, it's also fascinating. And now, the basics. An energy efficient home has 5 minimum essential characteristics: a well-insulated building envelope to minimize heat transfer, a well-sealed building envelope to minimize air infiltration, energy efficient windows and doors, an energy efficient heating, ventilating, and air conditioning system, and energy efficient appliances. This pie chart shows how energy is actually consumed in the average American household. And it illustrates quite dramatically where investments in energy efficiency are likely to produce the greatest payoffs. As you probably guessed, heating and air conditioning account for the largest share of residential energy consumption, by far. And that's why 4 of the 5 characteristics of energy efficient construction are focused in this area. So let's begin with insulation, a construction material that's used primarily to reduce heat transfer by conduction. Now, to understand how insulation works, we first need to understand the concept of thermal resistance, the extent to which a particular material resists the movement of heat through it. Thermal resistance is expressed quantitatively using a number called the R value. This equation shows how it's used. Suppose we're using a piece of 1/2 inch thick plywood as a partition between an interior room at 70 degrees Fahrenheit and the outside air at 30 degrees Fahrenheit. And we know that by definition, heat will flow spontaneously from the warm region through the plywood to the cold region. The rate of heat transfer is called the heat flux. And in the US, it's typically measured in BTUs, or British thermal units, per square foot of wall area per hour. Our values for all common construction materials can be found in handbooks and online. And for 1/2 inch plywood, the typical R value is 0.63. Thus, for this 40-degree temperature difference, the heat flux works out to 63 BTUs per square foot per hour. So what does this number really mean? Well, suppose this plywood wall is actually 8 feet tall and 8 feet wide. Then the total heat loss during a 24-hour period is 63 BTUs per square foot per hour times 64 square feet times 24 hours equals 97,500 BTUs. And the BTU is a measure of energy, just like a kilowatt hour. And using the standard conversion factor, 97,500 BTUs are equivalent to 28.6 kilowatt hours. At current residential electricity prices, that's about $3.50 in energy lost through our plywood wall in a single day. Now let's try insulating this wall with 3.5 inch thick fiberglass batting, here with an R value of 13. Thermal resistance is additive, so the total R value of the insulated wall is 13 plus 0.63 equals 13.63, and the heat flux falls to 2.9 BTUs per square foot per hour, which for our 8 foot by 8 foot wall is 4,454 BTUs per day. That's 1.3 kilowatt hours at a cost of about 17 cents. A very respectable reduction from the $3.50 in energy loss for the uninsulated plywood. That's how insulation works, and that's how the R value is used to measure its effectiveness. Warning, all R values are not created equal. This piece of fiberglass is R13, which means that its thermal resistance is 13 degrees Fahrenheit square foot hour per BTU. But if we bought exactly the same product in Europe, it would be R2.3. The actual thermal resistance is the same, of course, but expressed in international units, the R value is 2.3 degrees centigrade meters squared per watt. So when you're discussing energy efficiency with your European friends, be careful. Here's a table of representative R values in US units for a sampling of common construction materials and residential insulation products. Recall from our example that larger R values are better. Note also that these tabular values are per inch of thickness. Thus, for example, a piece of 3-inch thick expanded polystyrene foam would be R4 per inch times 3 inches equals R12. Now, several aspects of the data presented in this table warrant further discussion. First, although fiberglass batting remains the most widely used insulation in US residential construction today, there are many available products with superior thermal resistance. Moreover, fiberglass can be significantly less effective than even these R values suggest. Fiberglass is only really effective when it's properly installed. These bats must fit perfectly within the cavities of a stud wall, like this, and must be carefully cut and fitted around pipes, ducts, wires, and electrical boxes with no gaps whatsoever. Unfortunately, many contractors don't exercise this level of care, and the insulation's thermal resistance is compromised as a result. Just a 1/2 inch gap between the fiberglass and an adjoining stud or top plate can cut its effective R value in half. Of course, we could say the same thing about all types of insulation, that they won't work as advertised if they're not installed correctly. But there's a difference. Most of these alternative insulations are installed in ways that are much less susceptible to loss of thermal resistance. Let's look at one of the alternatives. This is loose fill insulation. It's typically installed by pouring or blowing the material into the cavity wall between studs and joists. Now, I can't demonstrate this without having the sheetrock installed, but I think you can see that because of its loose consistency, it's very effective at filling the spaces around pipes and wires and electrical boxes without any special fitting or trimming. And by the way, this particular material, this particular loose fill insulation is cellulose. It's actually made from recycled newspapers, and it has an R value comparable to that of fiberglass. Sprayed and foamed in place insulations are even better at filling tight spaces, and many of them have impressive R values as well. And finally, rigid board insulation is typically applied on the outside of the wall, as you see here, so there's no possibility of interference with internal utilities. The bottom line, it no longer makes sense to simply assume that fiberglass batting is the right answer for all of our home insulation needs simply because we've always used it before. Now, returning to our table, note that the R value for lumber is only 1.25 per inch. This creates a serious problem, a phenomenon called thermal bridging, which affects all types of insulation installed within the wall cavity. Let's investigate the phenomenon of thermal bridging using my model of a typical 2x4 stud wall. Notice that I have now added the sheetrock to the interior of the stud wall, and on the outside, we have some wooden siding applied over the outside of the oriented strand board sheathing. So with this wall system now complete, I'm going to tilt it forward so you can see the cross-section more effectively. And I now call your attention to this particular section of the wall. Heat moving through this section passes through, from outside to in, 3/4 inches of wooden siding, 3/4 inches of OSB sheathing, 3.5 inches of R13 fiberglass inside the cavity, and then 1/2 inch of drywall. Adding a small factor to account for the insulating value of the air layer along the external and internal surfaces, the total R value for all these materials along this path adds up to 15.6. Now let's look just a few inches away along this path through the stud. This path consists of 5 inches of solid wood, siding, sheathing, and stud, and then 1/2 inch of drywall. And so when we add it all together, the total R value along this path is only 7.6. This is a thermal bridge, and it occurs wherever studs, top plates, sills, or headers provide a low R pathway for heat transfer through the full thickness of the wall. Now, to determine the effective R value of this entire wall, we use an averaging procedure that accounts for the proportions of the total wall surface area corresponding to these two very different paths. And the result for the entire wall is R12. And this is a big problem because the 2015 International Residential Code requires that all exterior walls have a minimum of R13 in the southern US and R20 or higher elsewhere. The rather surprising implication is that the venerable, time-tested 2x4 stud wall with standard fiberglass batt insulation is no longer considered adequate for a home built anywhere in the US. Moreover, many green building advocates suggest that R20 is inadequate and that R24 or even R30 wall insulation is necessary for optimum energy efficiency. It's quite likely that the codes will continue moving in this direction in the years ahead. Today, builders are addressing this challenge in a variety of creative ways. One approach is simply to use higher performing insulation, like urethane foam, for example, within the wall cavities. This approach doesn't directly address the thermal bridging problem, but because the cavity accounts for about 3/4 of the wall area, insulating the cavity more effectively can push the overall R value high enough to meet the code. A more robust approach is one we've already seen, adding rigid foam insulation to the outside of the wall. Here, the continuous layer of insulation isn't interrupted by studs, sills, or headers, so thermal bridging is drastically reduced. And other types of insulation can still be placed inside the cavity to further increase the wall's R value. But without question, the most revolutionary approach to increasing the wall's thermal resistance can be seen in recent initiatives to re-engineer the wall itself. One such approach, called advanced framing, alters the most fundamental standard of traditional platform framing by replacing 2x4 studs spaced 16 inches apart with 2x6 studs spaced 24 inches apart. This change doesn't adversely affect the wall's structural integrity, but it greatly improves its potential thermal resistance by providing space for another 2 inches of insulation, while also reducing the proportion of wall area susceptible to thermal bridging. Advanced framing has the added advantage of reducing the total required quantity of lumber by about 25%, making it cheaper and even more attractive from a sustainability perspective. The disadvantage of advanced framing is that it's still susceptible to some thermal bridging. To address this shortcoming, some builders are now using 2 rows of 2x4 studs staggered like this to eliminate thermal bridging entirely, while also providing a 7-inch deep cavity for even more insulation. But perhaps the most effective approach of all is to eliminate wall framing altogether by using a technology we first encountered back in our lecture on residential structural systems, the structural insulated panel, or SIP. A SIP consists of 2 structural boards, typically oriented strand board, bonded to a solid foam core with total thickness ranging from 4.5 inches to as much as 12.25 inches, depending on the required R value. This particular panel is 4.5 inches thick, essentially identical to my sample stud wall, and it's a very impressive R26. The thicker ones can actually exceed R50. Now, as you watch this time-lapse video of a SIP house under construction, I think you can glean some of this technology's amazing array of advantages. SIPs serve as both structure and insulation. They can be used for walls, roofs, and floors. Because they have so few joints, houses made of SIPs are considerably more airtight than their platform-framed neighbors. SIPs are always custom fabricated in the factory or shop, so on-site they can be erected quickly with a small crew and a crane. And as soon as this structural shell is up, the builders have a fully enclosed, insulated space in which to continue their work. Now, like all technologies, SIPs have their drawbacks. Their fire resistance and sound attenuation are reported to be somewhat lower than conventional framing. At present, the upfront cost of building with SIPs can be somewhat higher than the cost of conventional framing, though the cost gap is narrowing as SIPs become more widely used. And when energy savings are taken into account, the life cycle cost of building with SIPs is typically 40% lower than that of framed construction. Its shortcomings notwithstanding, the structural insulated panel is a very impressive technology that's quite likely to see more widespread use in the future. Before we leave the subject of insulation, let's take a look at an element of the building envelope that's all too often forgotten: the concrete foundation. The thermal resistance of concrete is even worse than that of lumber. An 8-inch thick cast-in-place foundation wall has an amazingly low R value of 1.6. And because foundation walls and floor slabs are thermally connected to your building envelope, they can be a huge conduit for heat loss. That's why insulation of basement walls and slabs has now become commonplace in moderate and cold climates. Slab insulation is placed on the ground and around the perimeter before the concrete is poured. And foundation wall insulation is ideally adhered to the outside of the cast concrete after the exterior sealant has been applied and before the excavation is backfilled. In both cases, extruded polystyrene foam is generally used because of its good moisture resistance. No matter how well insulated your building envelope might be, its energy efficiency can be totally compromised by air infiltration, which can cause heat losses of up to 40%. Recall that the principal purpose of insulation is to resist heat transfer by conduction, but heat can also move by convection. And many installations, including all types of batting and loose fill, do little to prevent convection. Air infiltration is driven by three different physical phenomena. First, as we saw early on in the course, wind blowing across your house creates high pressure on the upwind wall and low pressure on the downwind wall. The air pressure inside your house lies somewhere between these two extremes. And since air naturally moves from high pressure to low pressure, the imbalance between outside and inside causes air to infiltrate from outside to inside on the upwind wall and from inside to outside on the downwind wall. Second, as we saw in the last lecture, forced air heating systems can cause similar pressure imbalances and similar movements of air through the building envelope. And third, within your home, hot air rises and eventually finds its way into the unheated attic space through gaps around light fixtures, attic access hatches, and such. And as the warm air escapes from the top of the building envelope, cold air seeps in somewhere below to replace it. Given these causes, minimizing air infiltration is simple in concept, but very challenging in practice. First, the building envelope should include a well-defined air barrier, typically consisting of exterior house wrap or rigid foam insulation, interior spray foam insulation, or well-sealed interior drywall. Second, the inevitable penetrations through the air barrier, for example at vents and outdoor faucets, outlets, and light fixtures, must be thoroughly sealed with caulk or sealant. Air leaks are also quite common at the intersections between different materials, like the joint between the subfloor and sill plate here, or between studs and sheathing, and these must all be caulked as well. But beyond these common locations, finding every possible leak in the building envelope would be virtually impossible if it weren't for this technology. Called a blower door, it consists of a powerful fan that's temporarily mounted and sealed within an exterior door frame. The fan sucks air out of the house, lowering the internal pressure and causing outside air to flow at high speed through any gaps in the air barrier. This air movement is then easily detected with a device called a smoke stick, and the gaps can then be identified and plugged. When used on a completed house, the blower door test can provide valuable information for an energy audit, but it's even more valuable before that interior drywall has been installed, when leaks can be more easily sealed. Windows represent a special challenge because they create discontinuities in both the insulation and the air barrier. As a result, windows are typically the largest source of heat loss in most homes. Modern energy-efficient windows respond to this challenge by purposefully addressing each possible mode of heat transfer: conduction, radiation, and convection. With respect to conduction, a single pane of glass has a thermal resistance of R1, Not quite as bad as a hole in the wall, but very close. And that's why energy efficient windows have at least two panes of glass, with a buffer of stagnant air in between. A double glazed window achieves at least R2 as long as that gap between panes is at least 1/2 inch. But heat can still move across that gap by convection. So the gap is typically filled with a heavy gas like argon to reduce convective losses. And to limit heat transfer by radiation, high performance windows use low emissive coatings, which reflect radiant heat back to the side of the glass where it originated while allowing visible light to pass. These so-called low E windows achieve at least R3, but with the addition of a third pane of glass and multiple low E coatings, a new breed of super windows are now able to achieve R values in excess of 10. As you might expect, these super windows aren't cheap, but having windows with thermal resistance comparable to that of a solid wall takes green building to a whole new level, while also opening up all sorts of new architectural possibilities. When you go shopping for windows, look for this label bearing the official certification of the National Fenestration Rating Council. The most important piece of information on this label is this number called the U factor, or thermal transmittance. The U factor is actually just 1 divided by the R value. Thus, this particular window with U equal to 0.33 has a corresponding R value of 1 divided by 0.33 equals 3.0. Now you may be wondering why windows and insulation use two different but equivalent measures of insulating effectiveness. Well, it seems that the U factor was defined by scientists and engineers for consistency with the process used to measure heat transfer. Heat flux is equal to the temperature difference times U. So it's convenient to conceptualize and to measure the U factor as the heat flux resulting from 1 degree of temperature difference. On the other hand, the R value was created for the more practical purpose of selling insulation. As we've seen, the thermal resistance is additive. The effective thermal resistance of a wall can be calculated by adding together the R values of its individual layers. This cannot be done with a U factor. So it really does make sense to use R for insulation calculations. Now, returning to our label, note that it provides us with several other quantitative ratings of the window's performance. The solar heat gain coefficient measures the fraction of solar radiation that's admitted through a window. It varies between 0, meaning no solar transmission of radiation, and 1, meaning 100% transmission. If the solar heat gain coefficient is low, it's probably because the window uses that low emissive coating we discussed earlier. However, we shouldn't conclude that a lower coefficient is always better. In fact, next lecture we'll see that windows with high solar heat gain are essential in certain circumstances. The visible transmittance here indicates the fraction of visible light that passes through the glass. If this factor is near 1, your interior will be brightly illuminated with natural light. If it's near 0, the window will act like a pair of sunglasses, keeping the interior relatively dark. Like solar heat gain, there's no good or bad visible transmittance rating. Rather, the coefficient should be selected for consistency with your planned use of the interior space. Some products also provide ratings for air leakage and condensation resistance. And the conclusions we can draw from these ratings are unambiguous. Higher air leakage is bad, and higher condensation resistance is good. Well, now we've installed high-quality windows with low air leakage in a well-sealed building envelope. But in minimizing air infiltration, we have almost certainly created a new problem: stale, unhealthy air. The air in your home can accumulate a wide variety of pollutants, including dust, combustion byproducts from gas ranges, water heaters and leaky chimneys, and hazardous gases emitted by various consumer products and construction materials. And as we've seen, inside air also acquires moisture from cooking, washing, showers, and people breathing. This moisture can condense on cold surfaces or inside wall cavities, causing rot and mold. For these reasons, mechanical ventilation is essential for any modern energy efficient home. The American Society of Heating, Refrigerating, and Air Conditioning Engineers sets the standard for residential ventilation at a minimum of 0.35 air changes per hour. In other words, 35% of your inside air should be replaced with fresh outside air every single hour. Old drafty homes usually achieve this standard without any mechanical assistance, which is why no one cared about mechanical ventilation until recently. But modern airtight building envelopes don't even come close to this standard without mechanical ventilation. Yet, bringing large quantities of outside air into an energy efficient house seems quite counterproductive. Why have we invested so much in sealants and insulation only to undo our efforts by pulling cold outside air into the heated interior space in the winter or pulling hot outside air into the cooled interior space in the summer? Well, the answer to this quandary is in this device, a heat recovery ventilator, or HRV, a combination ventilation system and heat exchanger. Here's what it looks like on the inside. The HRV uses two fans, one to exhaust stale air from inside to outside along this path, and one to draw fresh air from the outside to the inside along this path. In the center, where the two airstreams cross, is a heat exchanger, a series of intertwined passages that transfer heat from the outgoing airstream to the incoming one, or vice versa, while keeping the two streams separate from each other. The best HRVs can transfer up to 85% of the heat from the warm airstream to the cool one, thus achieving significantly better energy efficiency than the alternative forms of ventilation, an open window, or a leaky building envelope. I'll conclude with just a few words about our final two basics of energy efficiency. First, energy efficient HVAC equipment. In the last lecture, we discussed many aspects of efficiency in heating and air conditioning systems, but we didn't discuss the most important factor, getting the size right. HVAC systems can waste a lot of energy if they have too little capacity or too much capacity. Your HVAC professional can determine the required system capacity based on a calculation of the total heating and cooling loads for your house. But don't forget that the heating and cooling loads will be substantially reduced by improved insulation and sealing and by high-performance windows and doors. So it's essential that these enhancements to the building envelope be planned or implemented before the capacity of the HVAC system is determined. If not, you'll probably be buying more capacity than you really need. As our graphic of residential energy use shows, selecting energy-efficient heating and air conditioning systems can produce energy savings in the largest slice of this pie. But choosing energy-efficient appliances can produce savings in all of the other slices. The challenge, of course, is that all of these slices of the pie represent a very large number of appliances, and making smart choices for all of them can seem like quite a daunting task. Fortunately, this task has been greatly simplified by the Energy Star program, a joint initiative of the U.S. Department of Energy and the Environmental Protection Agency. This program sets strict standards for energy efficiency, and so Energy Star rated appliances typically use 20 to 30% less energy than their non-rated counterparts. Through the simple commitment to buy Energy Star devices, including HVAC systems, we can effectively shrink the entire energy pie for the good of the planet and our household budgets. In the next lecture, we'll take energy efficiency to a whole new level as we explore one of the most fascinating dimensions of the green building movement, passive solar design.